Hello everyone, my name is Maliyov and I'm going to tell you about the ultrafast electron dynamics in the Boltzmann transport equation framework. I will discuss the general theory as well as its implementation in our Perturbo-code. So, with the growing computational power, nowadays it's possible to perform the real-time ab initio dynamics simulation in a large variety of fields, and one of the methods to do that is the real-time time-dependent density functional theory presented here on the left. So here we perform the propagation of the time-dependent electronic wave function phi according to the time-dependent Kohn-Sham equation. So you can see this equation here. A typical time of these simulations is about 1 attosecond. So in most of cases, it's a quite an accurate computational approach. However, due to its computational burden, one cannot perform the simulations longer than femtoseconds. So here, the region that covers times from attoseconds to femtoseconds is depicted in blue, and this time scale corresponds to the electron-electron interactions. So, in fact, there are a lot of important physical phenomena that occur in larger time scales. So, for example, electron-phonon, phonon-phonon interactions, etc. So, in order to describe these interactions, we need to go in the larger time scales, and one of the methods to do so is the many-body perturbation theory to compute scattering processes. So here we solve the time-dependent Boltzmann transport equation, and now we perform the propagation of the electron populations functions, a function f. And a typical time of these real-time simulations is about 1 femtosecond. So it was the total simulation time in the previous approach, just to give you a comparison between the two. And in this lecture, we will consider the second approach, so the real-time dynamics within the Boltzmann transport equation. Okay, so let us consider in detail the Boltzmann transport equation. So here it is in the center. And so it's basically a statement on the conservation of the number of particles in phase space. And hereafter we will apply the following assumptions to this equation. So we will assume a homogeneous material. So that's why we will not have the R derivative over here. We will also assume no external fields, which will cancel out as this third term on the left-hand side. So this is not a necessary requirement to the Boltzmann transport equation. And currently we are working on including this term in the Perturbo-code. So in future releases, we will have this term in the equation as well. So, and Boltzmann transport equation is a differential equation, and as for any differential equation, we need to provide an initial state. So here we need to provide an initial condition f at t equal to 0. So on the right-hand side, we have the collision term, which can describe a lot of different collision processes. So for example, electron-phonon, electron-electron, electron defect, etc. But in this lecture, we will consider only the electron-phonon scattering processes. Therefore, we will have the electron-phonon scattering integral, which will depict here, I electron-phonon, and it's actually a functional of the electron occupation function f. So here we have our equation, and roughly speaking, on the left-hand side, we have a part that describes the electron occupation function, and on the right-hand side, we have the electron-phonon scattering physics. So on the electron side, we have the electron distribution function f and k of t, where k is the electron momentum, and its electron band index, and t is time. On the phonon side, we have the phonon occupations n nu q, where q is the phonon wave vector, nu is the phonon mode index, and here we will consider the fixed phonon occupations at desired temperature. So it means that we select one temperature, and then we assign a phonon occupation that corresponds to the Fermi-Dirac distribution. And again, it's not a necessary requirement for the Boltzmann transport equation, and also in our group we are working on the description of both time-dependent electron occupations and phonon occupations. But here for this lecture, we will consider the phonon occupations fixed. Okay, so as you can see, the term that describes the scattering physics is this electron-phonon scattering integral. And one of the main ingredients is the electron-phonon matrix elements. So I will start describing in more detail Boltzmann transport equation, starting with the electron-phonon matrix elements. So let us first consider an electron at its initial state Nk, and we assume that it undergoes a transition to the final state Mk plus Q, and it emits a phonon with the frequency omega. So then the electron-phonon matrix element will give us the probability of scattering from this initial state to the final state. So here's the expression of this electron-phonon matrix elements. So we have the initial state psi nk, we have the final state psi mk plus q, and here in the for the operator we have the phonon mode resolved perturbation potential due to the lattice vibrations. And in Perturbo we first calculate this electron-phonon matrix elements on a coarse grid from DFPT, and then we perform a very efficient interpolation on fine grids in Perturbo. Okay. So now, in order to derive the electron-Boltzmann transport equation, let us consider in detail these scattering processes. So here we go into consider them. We have a lot of elements here, but let us first start from the top left element here. So again, we consider a scattering from initial state Nk to the final state Mk plus Q. So this process can occur actually if we have some electrons in the initial state Nk. So we have that's why here we have this occupation function f. Then the electron can undergo this transition if we have some empty states at the final state. So the empty states would correspond to the 1 minus occupation function of the final state. And then, since we emit a phonon, we will multiply this term by n plus 1. So plus 1 because we can always emit one phonon. Okay, then let us consider a time reversal conjugate of this process. So it will be an electron which undergoes a transition from the final state to the initial state and absorbing a phonon. So that's why we will have the electron occupation functions mk plus q multiplied by the function that corresponds to the empty state at the final state. So we basically just interchanged these occupation functions, and then since we absorb a phonon, now we multiply by simply n. Okay, so as well we need to take into account the energy conservation of this in these processes. So we can easily see that this process can happen if the initial energy is equal to the final energy plus the phonon energy. So this is the conservation law. And so we can multiply by the corresponding delta function of this term. Okay, then as was discussed in the previous slide, we should multiply by the probability of scattering that takes into account the initial state and the final state, G. Okay, and we will call the overall term here as F emission. So now let us consider similar scattering processes, but with the phonon absorption. So again, we consider initial state Nk, final state Mk plus Q, but absorbing a phonon. So now our derivations will be very similar, but here we will have the n, not n plus 1, but just n. And again, considering the time reversal conjugate, we will have the similar conclusions to derive this term. Okay, then we take into account as well the energy conservation and the probability of scattering. And we will call this term here in brackets as F absorption. So finally, we can construct our total electron-phonon scattering integral if we sum over all band indices, electron phonon momentum, and phonon modes. So here, all this sum would give us the electron-phonon scattering integral. Okay, so so finally we have this time-dependent Boltzmann transport equation with the electron-phonon scattering processes. So here it is. It's time-dependent. You see this derivative here. And the computational challenge is that we have seen that these terms F emission and F absorption, they depend on time. So they depend on occupation function f, which depends on time. So they are time dependent. It means that for each time step t, we need to re-evaluate, recalculate these terms, which is very computationally challenging. So in order to solve this equation, of course, we need to select a time-dependent, time propagating algorithm. So we can pick just the first order Euler. So in this case, we would just replace partial f partial t with delta f over delta t, and we can get this simple expression of the occupation function at the next time step as a function of occupation function nt plus the electron-phonon scattering integral, or we can use more accurate but also more computationally expensive fourth order Runge-Kutta method. So, and of course, we just cannot perform this propagation for real system without the efficient OpenMP and MPI parallelization. And I will discuss in detail this parallelization in the next slide. But another solution that could decrease the computational cost is the selecting the energy window. So let us, to demonstrate that, let us consider silicon band structure here. So here it is. And let's consider that we are, for the moment, we are interested in the electron transport. And we are not going to excite our system too much. So then we would select an energy window of interest. So just electron bands, and not all of bands, but some, just so bands of interest. So then we can select this energy window from the input file in Perturbo, so that we can restrict the number of k points. So we can have a drastic decrease of the total number of k points in this case. Okay, so now let us consider in more detail the OpenMP and MPI parallelization. Okay, so here again we have this equation, the time-dependent Boltzmann transport equation, and I would like to describe you schematically in more detail what happens in on the MPI and OpenMP parallelization. So we start our simulation with some initial time, let us call it t0, and then first thing we do is to find, select, and distribute the KQ pairs. So it means that we select only those KQ pairs that satisfy the energy conservation within a threshold. All other KQ pairs would not be would be rejected. So this will always also save us the computational time. So once we selected all the KQ pairs of interest, then we will redistribute them over different MPI processes. So I call it process 1 to up to n. Okay, so for each process, we will have the local set of KQ pairs, and we will calculate the electron-phonon matrix elements for these KQ pairs. And then, having these electron-phonon matrix elements, we will evaluate the electron-phonon scattering integral. So we will perform the partial sum over the local KQ pairs to perform this summation. And all what happens in this block, this schematic block, is also parallelized in OpenMP. So we have, for this computation of the electron-phonon scattering, electron-phonon matrix elements and scattering integral, we have also the parallelization over the OpenMP threads. Okay, so once we perform the partial sum, we can collect the results from all different MPI processes and evaluate the total electron-phonon scattering integral. So this is great because if we know our electron-phonon scattering integral at time t, then we can solve the equation and find our occupation function at time t plus delta t. And then we simply continue our simulation. So we repeat these steps with one particular point is that once we already calculated these electron-phonon matrix elements, so these terms do not depend on time. It means that we will not, we do not need to recalculate it each time at our simulation. So it means that we will simply reuse our electron-phonon matrix elements, and we will restart our process from this point. Okay, and then we will continue our algorithm while the total simulation time is not reached. Then we finish our simulation. So then, in order to show in more detail the parallelization performance, I would like to show you a test case. So for the test case, I've selected gallium arsenide with a typical calculation. So the grid is not too big, but also not too small. So it's about 120 cube K points. And you can see that, and also I applied an energy window restriction for the electron transport regime. And you can see that even for typical calculations, the number of KQ pairs is very big. So that's why we need this efficient parallelization. So as for the computational setup, I used 4 nodes and 80 cores in total, so 20 cores per node. So what I would like to show here is the time of one real-time dynamics iteration on y-axis as a function of MPI processes per node on a bottom x-axis, as well as number of OpenMP threads per MPI process on the top x-axis. So the key idea here is that I keep the number of cores constant. So I keep my computational resources the same for each point on this curve. So if I increase my MPI processes, that means that I decrease my OpenMP threads. And then you can see that if we change the balance between the OpenMP threads and MPI processes, we can see that we have the best combination, which corresponds to 4 MPI processes per node and 5 OpenMP threads. And this result is, of course, machine dependent. So it depends on the architecture, so how many sockets are in each node and how many cores are and how efficient is the communication between the cores and between the sockets, etc. So it depends on many factors. But the trend would be the same on your machines as well. So the trend is that both MPI and OpenMP parallelizations are important, and somewhere in between, somewhere where both MPI and OpenMP are involved, you would have the best time. And this kind of test is not time consuming, so you can pick a test system, not perform two large simulations. You basically need only one time step for that. And you can do this very easily, this type of calculations, to evaluate the best combination for your machine and for your computational purposes. Okay, so now I would like to switch to a physical example to see some physical results. And for this example, I've selected silicon. And so here, what we are going to do is to excite a system. So as I explained in the first slide, we have an initial condition to our differential equation. So our initial condition would actually correspond to an excitation. And in this case, we would like to excite our system with a Gaussian excitation around the energy E0. So we can see this Gaussian excitation here. So in this plot of electron population as a function of energy. Okay, so I performed these calculations at the room temperature at 1 femtosecond time step and with simpler Euler propagator. So talking about the solvers or propagators, so here I've selected Euler because for this example, for silicon and 1 femtosecond time step is a well-behaving system, and we do not need very precise solvers. However, in different cases, you can imagine scenarios where using a more accurate Runge-Kutta solver would be very important also. But here Euler works very well. So now we can see the time-dependent simulation. So what we actually can see is the relaxation of electron occupation from the Gaussian excitation to the Fermi-Dirac distribution that corresponds to the given temperature, so room temperature in this case. Okay, so now I would like to come to conclusions. So I would like to say that in Perturbo, it's possible to perform the ab initio real-time ultrafast electron dynamics for the electron-phonon scattering processes. It adopts the efficient hybrid OpenMP and MPI parallelization. And the real-time simulations are very flexible in sense that you can excite your system in many different ways. The excitations that are already implemented in Perturbo are Gaussian, Lorentzian, and Fermi-Dirac, but you can implement your own type of excitation in the code, so it would not be very complicated. So typically it would be a couple of lines or maybe 10th of lines, but not more. And so you can select the energy window and bands simply from the input so that you can optimize the computational time for your needs. You can perform both electron and Hall simulations separately. And also very useful feature is that you can restart simulations. So you can perform your simulation up to some time t. Then you can realize that you need maybe to perform the simulation even longer to converge some quantities or for another reason. So you can just simply restart from that time moment. And on the output, we produce the HDF5 output data format, which is cross-platform and which is very useful to manipulate with. So we can, for example, perform this one part of calculations and send this file to another collaborator who works on another machine, and it would be possible to continue these calculations. And due to the efficient parallelization as well as energy windows and other techniques, we can reach very long time scales. So up to hundreds of picoseconds and sometimes even nanoseconds with the femtosecond resolution. Okay, so with this I will finish my presentation, and thank you very much for your attention.